Hello everyone, welcome back to another video from the series, and today I decided to solve one IMO problem as I promised, and it's from 2023 IMO problem number 4. And because it's number 4, it should be easier than other like 2, 3, and 5, 6. So I thought it was quite doable, so I tried it on my own first, and apparently I was not able to solve it. So I will just quickly share the insights that I got. So because after looking at ASOP 2023, like this number is quite big, so I was like, wait, what if we use induction? We might be able to prove it. So like, because we know that 2023 is like somewhat similar to 2023 times 3 over 2. So maybe like we can prove that a sub n is always greater than or equal to n times like something like 3 over 2 or minus 1 or something like that, because it's quite similar, I think. And wait, what do we get when we calculate this? We get 1000.5 times 3, which is 3004.5. Yeah, so I think oh sorry, I forgot to put 0 here. Yeah, so like I thought this was quite a reasonable idea, so I tried it. So what I did is I just like started my base case. I know this is equal to square root of x of 1 times 1 over x of 1, which is 1, which is clearly greater than or equal to 1 over 2. So our base case works. But we need to continue trying because we don't know what will happen. So this one is equal to times 1 over x of 1 plus 1 over x of 2. Now we know that this should be greater than 2 using our Cauchy-Schwarz inequality. However, I'll elaborate more on this in the later solution because this is actually the correct idea to start with. And also it's not greater than or equal to because x of 1 and x of 2 are not equal to each other. But then I realized that yes, so this is still true. This is still greater than or equal to 2. So our base case and other cases are true. However, the problem is, like, let's say that this thing minus 1, this is true, then we need to prove that then this one is also true. And since our base case work, it will work. However, I was not able to move on from here. Maybe because, so let's rewrite this a little bit. So this is greater than or equal to 3 over 2 times n, and then minus, let's say that this is 5, right? 5 over 2, yes. Let's say that this is true. Now, then how do I prove that a sub n is greater than n times 3 over 2 minus 1? And yes, that was actually my problem. So yes, that was, I couldn't like continue. I was wondering if I can like try and write a few more terms here and there, but that actually ended up being really messy and I was not able to continue my solution. So I had to stop from here and look at the solution. So that's quite sad, but yes. So this is the official solution that the IMO released, and I'm not going to like copy and paste their solution. I'm going to include some of my insights. So if it seems quite different, please be understanding because it will be the same ultimately. And so we can do our basic observations here. We know that a sub 1 is equal to square root of x of 1 times 1 over x of 1, which is equal to 1. Now let's try a few cases like a sub 2 because we want to observe something. So we know that a sub 2 is equal to x sub 1 plus x sub 2 times 1 over x sub 1 plus 1 over x sub 2. And notice that using Cauchy's inequality, we know that x sub 1 plus x sub 2 times 1 over x sub 1 plus 1 over x sub 2 is greater than or equal to 1 plus 1 squared, which is equal to 4. However, notice that x sub 1 and x sub 2, they are different. So therefore, this whole thing, x sub 1 plus x sub 2 times 1 over x sub 1 plus 1 over x sub 2 is greater than 2. 4. So therefore, a sub 2 is greater than 2. So this is what we know so far. When we continue doing this, continue using Cauchy's inequality, we can prove that a sub 2023 is greater than 2023. However, that's not what we are finding, so it's oops. So actually this thing, I also tried it and I couldn't continue from here too, so that's why I just showed up till here. And now one thing that we can observe from here is actually the same observation that I had. So we know that 2023 times 3 over 2 is somewhat similar to 3034. And one brilliant thing that the people did here is this thing is somewhat similar to 2023 times 1 over 2 plus 2023 times 2 over 2, because I just rewrote the equation. Now all we can do here is we can rewrite it as 1 plus 1011 plus let's just say that 1011 times 2 and times 1 here. Now, actually from here we know that they are equal to each other because it's 3033 plus 1, which is equal to 3034. Now this is quite of a brilliant observation here, because we know that a sub 1 is equal to 1. So a sub 1 plus 1 times 1011, so we add 1011 times and add 2 1011 times, then we get 3034. Now then one observation that we can have here is, let's say that we have our sequence. We continue on to a sub n. So we know that this thing is equal to 1. So we add something. We add 1 here. We add something greater than or equal to 2. We add 1 again. We add something greater than or equal to 2. And if we continue doing that, then we will eventually notice that a sub n is greater than or equal to 3034, or a sub n, not 3034, will be greater than a certain number following this pattern. So in this case, it will ultimately result in this case. Now, if you want to be more algebraically precise, that's what we're going to do right now, because that's quite important. Let's write our lemma. So based on this observation, we know that, let's say that if the two previous terms has the difference of 1, if this thing is true, then the next one, a sub n plus 1 minus a sub n is greater than or equal to 2. So what we can do, if this is true, then the reason why we wanted to do this is because we know that a sub 2023. So I just know they just changed this idea into this lemma, because we can manipulate algebraic numbers. Algebraically more readily if you do this. So this is simply equal to a sub 2023 minus a sub 2021. I think for me it was quite brilliant, but I think to other people it's just quite normal thing to do. So meaning I need to study more. Minus a sub 1 plus a sub 1. Now this we can say that how many terms are there? Like I mean how many groups? We have 1, 2, 3, and then we have 2023 groups, right? So we know that this is equal to or greater than or equal to 1 plus this 1 is from a sub 1, and 1 times 1011, because let's say that because if our lemma is true, if this thing is true, if the half of them, like we have 2022 numbers left, right, and the half of them have the difference of 1, and then the other half will have the difference of 2 or something greater than that. So therefore we can write that a sub 2023 is greater than or equal to 1 plus this thing. And notice that 3034 is equal to that number. This is actually equal to 3034. So therefore if we prove our lemma, then a sub 2023 is greater than or equal to 3034, which completes the problem. So let's start the proof for our lemma. So let's prove our lemma, and before proving that, I just quite want to rephrase it a little bit, because I think there is a better way of doing it. No, maybe I think it's totally fine to do this, but I just want to avoid the use of -1 here, like -1. I don't like that. So yes, let me rewrite the lemma again. And even though I rewrite the lemma, it will still be the same, because you're saying the same thing. So if a sub n plus 1 minus a sub n is equal to 1, then a sub n plus 2 minus a sub n plus 1 is greater than or equal to 2. Now let's prove our lemma. We first want to find the relationship between a sub n plus 1 and a sub n here. So let's square it. So what is a sub n plus 1 squared? And the reason why we want to square this is because if we square this, then we can find an equation that contains both the terms a sub n plus 1 and a sub n. Yeah. So by definition, this thing is equal to x sub 1 plus dot 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 plus x sub n plus 1 times 1 over x sub 1 plus dot 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 plus 1 over x sub n plus 1. So this thing is true. Now, as I mentioned before, we want to write this in terms of like a sub n. We want to include a sub n here. So what if we rewrite our thing like this again? Because notice that this thing will just simply be equal to a sub n squared. So plus, we multiply them, we need to multiply these. So x sub n plus 1 times x sub 1 plus dot 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 plus x sub n. And then we have this one, and these two times x1 plus dot 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 plus 1 over x sub n. And finally plus 1. So this is equal to a sub n squared plus 1 over x sub n plus 1, x sub 1 plus dot 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 plus x sub n. And we have x sub n plus 1 times 1 over x sub n. Sorry, 1 plus dot 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 plus 1 over x sub n. And then plus 1 here. And notice that there's something brilliant that we can do, and that is using AMGM inequality here. The reason why we want to use AMGM inequality here is because if we use AMGM for these two, we can cancel out these two terms and have a term with a sub n, right? It could be a sub n squared or just simply a sub n. So we know that this is greater than or equal to a sub n squared plus 2 times square root of these things multiplied together. So times x sub n plus 1, and then multiply x sub 1 plus dot 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 plus x sub n, and we have 1 over x sub 1 plus 1 over x sub n, and then plus 1. And notice that these two cancel out, and this thing is just simply equal to a sub n squared. So, a sub n. We have 2 here, so don't forget that. And this is equal to, or greater than or equal to a sub n plus 1 squared. Now, before proving our lemma, we just found another relationship that a sub n plus 1 squared is greater than or equal to a sub n plus 1 squared. Now notice that, so we want to find a case where a sub n plus 1 is equal to a sub n plus 1. So then, and the reason why we want to find this case is because if we say that this thing is true, then by contradiction we can say that a sub n plus 2 minus a sub n plus 1 is equal to 1. So if this is true and this is true, and if we somehow find a contradiction, then we prove that our lemma is true and we can finally solve our problem. So that's why we want to find a case when they're equal to each other, because there might be a case, and also we're saying that if this thing is true, then this is true. So when are they equal to each other? They're equal to each other when these two are equal to each other, right? Using AMGM. So so it says if, right? If a sub n plus 1 is equal to a sub n plus 1, then if this thing is true, then this is saying the same thing as when 1 over x sub n plus 1 times x sub 1 plus is equal to x sub n plus 1 times 1 over x sub 1 plus dot plus 1 over x sub n. So if this thing is true, then a sub n plus 1 equals a sub n plus 1 is equal to each other. So they're actually saying the same thing. So if this is true, now we can do the same thing for this one. And for this one, we can just add add a few more terms. So plus 2 plus 1 is equal to x sub n plus 2 times 1 over x sub 1 plus 1 here. So so this thing, wait, what? So this thing is saying the same thing as the second one. So if the first thing is true and if the second thing is true, then our lemma is wrong. However, if the first thing is true but the second one is wrong, then our lemma is true and thus prove. And the reason why there are no other cases than that is because if a sub n plus 2 is equal to 1 plus a sub n plus 1, these two cannot be equal to each other. They never can be equal to each other because x sub I is positive numbers. And also, if this is not true, then this should be greater than or equal to 2 plus a sub n plus 1. And this is totally fine. That's yes, that's totally fine. So there are 3 cases. If this thing is true, then there are 3 cases, these 3 cases. But this doesn't work, so it leads to 2 cases. So now our concern here is, what if this thing is true, not this one? Then we are now trying to prove that this can never be true. so that this must always be true and thus prove our lemma. So from here, let's say we know that this thing is true, and for the sake of contradiction, let's say that these two are both true. And then if we have any contradiction, then we will be done. Is there any ways to somehow use our first equation to second one? Maybe there is a way. Maybe like x of 1 plus dot 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 plus x of n, because it ends for x of n here, plus x of n plus 1 over x of n plus 2 equals x of n plus 2 times 1 over x of 1. And we're doing the same thing because we want to somehow utilize this. Plus x of n plus 2 over x of n plus 1. Okay, so this is just a direct consequence of the second equation. Now, what can we do? What can we do? I think why don't yeah, actually, why don't we try and factorizing them, like x of n plus 2, like this. Forgot my parentheses here. Plus x of n plus 1. Ah, yes, this works. So x of n plus 2 times 1 over x of 1 plus 1 over x of n plus 1, right? Now we can actually factorize it again to lead to this form. So x of 1 plus x of n over x of n plus 1 plus 1 is equal to the x of n plus 2 over x of n plus 1 times x of n plus 1 times 1 over x of 1 plus plus 1 here. Now we know that these two are equal to each other, so therefore if the first thing is true, then what am I writing? It's equal to x of n plus 2 over x of n plus 1, and therefore x of n plus 1 is equal to x of n plus 2, and this is a contradiction. Therefore, if the first thing is true, and then the second one cannot be equal or cannot be true. Therefore, x of n plus 2 is always greater than or equal to 2 plus a sub n plus 1, and that proves our lemma and thus completes our problem. So I think this was pretty interesting problem for me because there are multiple kicks. And the first kick is noticing to try and use cost-short inequality here. That was our first one. And the second one is trying to rewrite 3034 by using 2023. So that was our second kick right here. And then trying to notice the pattern and then writing that algebraically, our lemma here. That was our third kick. And then using contradiction, like finding this to prove our lemma and complete the problem was our fourth kick. So I think this problem was really interesting to me, and I really enjoyed learning about this problem. I hope everyone did. And tomorrow I will be back here with another fun problem. I hope all of you guys will enjoy it. Then thank you for watching the video and see you tomorrow. Bye.